Hey, this is Horner, and this is the multiple choice pretest review for rotational motion. And we're going to look at questions number 11 through number 20. We have a bowling ball of mass m and radius r, whose moment of inertia is 2/5 mr squared. So remember, you don't have to memorize those. They will give them to you. So it rolls without slipping along a level surface at speed v. The maximum vertical height to which it can roll as it ascends an incline is, and then you have to determine which one of these is going to give the correct height. For a ball that's rolling, we know that if it's rolling to the right, there is linear displacement. So we know that that is just the change in x. We also know that it's rolling, and when it rolls, we know that we also have a change in the angle. So if I have a velocity, I know that I also have an angular velocity. I have both of these velocities. I have the velocity in a straight line, and I have the velocity of this ball in terms of its angular velocity. So we're going to have to take the angular velocity that we find for the ball and make it into linear. And if you remember, the equation we'll use is v for linear velocity is equal to our angular velocity, which is omega, and then we just multiply times the radius. And so that's how we convert from one to the other. So let's go back to the problem, kind of think about it for a second. Ball goes until it gets to an incline, and then it stops at the incline here. So that's the final position. Here's our original position. Our original speed, they said, is v. And then when it gets to this height, we know that our final speed is going to be equal to 0. It also has an original omega speed, and a final omega speed here would also be equal to 0. So notice that it has this regular speed starting, but it also has a speed of rotation. So as it rolls, it has an angular speed, and it's got a speed going left to right and then up the hill. So what does that mean? That means that it has a kinetic energy at the bottom, and then at the top, the kinetic energy is equal to 0. So at the top, it has an energy due to gravity, and at the bottom, we're going to call this height equal to 0 down at the bottom. So there is no gravitational energy at the bottom. So let's use conservation of energy, and we know that the kinetic energy at the bottom should be equal to the potential energy due to gravity at the top. So if that's true, let's go ahead and set up this kinetic energy equation. We know that it's got both linear and it has angular kinetic energy, and the equation for linear kinetic energy is 1/2 mv squared, and for angular is 1/2 I omega squared, where I is the moment of inertia, so that's this value, and then the angular speed we know is just the radians per second that it's turning. So let's go ahead and add these two together, and that will give us our total kinetic energy at the bottom. So we're just going to put KB here for kinetic energy at the bottom. The issue that we have with this is we need to get it into one type of term, so we really want to get it into V. Into linear terms instead of angular terms. So let's go ahead and flesh this out. We have 1/2 mv squared plus 1/2, and then we need to put in the moment of inertia, so that'd be 2/5 mr squared. And then we need to remember we've got to convert this omega to velocity. So here's our equation to do it. If we go through and think about it, we really have omega is then equal to V over R. We've got to use a capital R here. So that would be V squared over capital R squared. So that's what this is. This term right here is now this term. We can go ahead and cross some things out now. So we're going to cross off the mr squareds. I'm sorry, the r squareds, leave the m's. And now we have 1/2 mv squared plus 1/2 times 2/5 m times v squared. Let's go ahead and multiply these. So we have 1/2 times mv squared plus 1/2. Oops, sorry. I want to go ahead and multiply here. So I'm going to take that 1/2 and multiply it times 2/5. That gives me 2 over 10 mv squared. And if I go ahead and combine these terms, I know I have to multiply this side by 5 over 5 so that I get a 10 on the bottom. So that would be 5 tenths plus 2 tenths will give me 7 tenths mv squared. So that's my kinetic energy. Potential energy due to gravity is really easy. It's just mgh. So now I can get rid of my m's and I can solve for h. If I solve for h is going to be equal to 7v squared all over 10 times g. And that is this answer right here. So it would be letter D. That's number 11. Pretty long problem to get just that little bit, but that's how it works out. For number 12, it says, in which of the following diagrams is the torque about point O equal to the magnitude of the torque about point X in the diagram above? So we know that for torque, remember torque is just equal to force times the radius, and the radius here is L. So we need to figure out which one of these is equal to F times L. Here we've got 2F times L, so that one can't work. Here we've got F times L over 2, so that one can't work. It's either got to be this answer or this answer. It's usually never none of the above. However, every once in a while they do that. The tricky thing about this problem is they have not given you the right angles. This angle is incorrect. We really want the angle that goes with the horizontal component. So this angle right here is what we want. It's 30 degrees, so we can get rid of this. And then they gave us 30 degrees down here, and we really want this angle with the horizontal, which is 60 degrees. So we're going to get rid of the 30. Now we can use our equation for torque. Remember, torque is equal to force times R times the sine of the angle. Here, the sine of the angle was 90, so that makes this 1, so it's really just FL. So let's see if either of these will give us that. If we go ahead and we take this one, let's do the one with the 30 first, see if it works out. So this is equal to 2F, so I'm going to put in 2F, because that's the force, times our length, times the sine of 30 degrees. Now the sine of 30 degrees is actually equal to 1/2, and if I cross off my 2's, aha, there's the answer. It is FL, just like the original torque, so our answer is letter C. And that one really looks complicated, but boy, it was really super easy when we finally kind of think about it. So we're looking at number 13 now. Has a particle of mass m. It's moving at a constant speed to the left, and it's going along this dashed line that is where y is equal to a. So when the particle is at this point, we want to know what is the angular momentum and in respect to the origin. So this is one of those weird problems that we did with the 3 points, but we're going to look at this origin. So instead of going to the right this time, this one's going to the left. We know that we have a radius right here. So here's our radius, and what we'll do is we're going to say the angular momentum is equal to m times v times r, and then it's also times the sine of the angle that we are looking at it at. So if we're standing here and it's going up and this is our direction of motion, our angle theta is this angle right here. Okay. If I think about this, sine of the angle, if I take the radius times the sine of the angle, that gives me this position right here, which is A. And so this one's really kind of easy if we think about it. If r times sine of the angle is A, our answer is simply just mv times, and then we said this is A, so we're just going to put A. So remember, if I take r times the sine of the angle, that gives me this side, and so our answer is simply just B. So that one's just nice and easy to do. The next one that we need to do is number 14. It says we've got a square piece of plywood on a horizontal tabletop. It's subjected to 2 horizontal forces, and they want to know where should a third piece be, where should a third force of magnitude 5 newtons be placed in order for this thing to be put into equilibrium. So in equilibrium, we know that this thing has got to be going at 0, so we don't want any torque at all. We want the torque to be essentially just 0 altogether. So where do we put that 5 Newton piece in order to make it 0? Right now we know that it's rotating clockwise when I push on it with 5, and at 10 where it's pushing straight up. So we notice that really there's no torque here about the center at all. So this one is really irrelevant. We don't need to even pay any attention to it. So now let's just pay attention to the 5 Newton force. When it pushes, it makes it rotate this way. So we need an equal and opposite force in the other direction, and that would be a 5 Newton force right here. And so you'll look through your answers and notice the only answer that you can do is letter A. So that's it. Let's go ahead and go on to the next part. So this is number 15. For number 15, we have a uniform rigid bar of weight W is supported in a horizontal orientation as shown above by a rope that makes a 30-degree angle with the horizontal. So this is a bar, we've tied a rope to it, and we're just pulling on that rope so that it's going up in this direction, the pull is, and so therefore it holds the bar level. The force exerted on the bar at part O, which is pivoted, is best represented by a vector whose direction is which of the following? So for this one, the easiest way to think about it is we know that we have a force going up and to the left on this bar, so we also need a force going up and to the right in the opposite direction at the same angle in order to hold that position steady. So the only answer that you can use here is letter B. Now there is more to this one, but I think the easiest way to look at it is just think about how would we hold it if we didn't have that little piece, because essentially all that piece is allows it to pivot. So that's exactly what that point O is doing, is it's using a force going in this direction. It just counteracts the force that's pulling on it. If I lowered the angle down to 25, then the angle that the pivot would make would be also that 25 degrees. So really just not a lot to this one. For the next problem, which is number 16, let's clear this off here. Come on, clear out. It's thinking about it, it's just not doing it. So for number 16, let's see if we can get this to clear a little bit better. For number 16, it says a uniform stick has the length L. The moment of inertia about the center of the stick is IO. So a particle mass M is attached to one end of the stick. The moment of inertia of the combined system about the center of the stick is equal to the sum of the moment of inertia of the stick and the moment of inertia of the particle. Remember the moment of inertia of a particle, so that's just equal to mr squared. That is on your equation sheet, so you really should recognize that. Let's think about the stick now. So here's our stick. We know that it has a length of L, and it's rotating about the center. So we're going to put our center right here. That means that if we have a mass over here of m, that the distance from the dot over to the x is going to be L over 2, and that'll be really important, and that'll be equal to our R. So let's go ahead and do this one now. So we know that the moment of inertia total should be equal to that original moment of inertia, which is the moment of inertia of the stick, plus we've got mr squared, which is the moment of inertia of this mass. We've got to put everything in the right directions now, so we've got IO plus M, and then remember R here is really L over 2, so this is going to be L over 2, but we've got to square that. At this point I've got IO plus, and now I've got 2 squared is 4, so this would be 1/4 of ML squared. And our answer then for number 16 has got to be letter A. For number 17, it's the next problem here. We do have a long rod, and this rod is very light, and so because it's so light we don't have to worry about its moment of inertia. It is pivoted about the horizontal axis as shown, so pivoted right here. When released from rest, the rod begins to rotate with an angular acceleration of magnitude, so we've got to figure out what that angular acceleration is. The easiest way to do this one is to first assume that the pivot is frictionless, so that it can pivot. And we've got to go through and think about the two torques. We've got a counterclockwise and a clockwise. This is our counterclockwise, so this would be a positive torque. We're going to call it torque 1. And then we've got a clockwise torque here, which would be torque 2, and it's negative, so negative torque 2. Those two torques then will give us acceleration. So at this point, what we're going to do is let's go ahead and find our equation for the sum of the torques. So let's find out what the total torque is. So the sum of the torques is equal to torque 1 plus negative torque 2. Torque 1 will be 3, so our force here is 3 times MO. Really, I guess that what we need to do is we've got to remember that torque is really I, okay, here times our angular acceleration. So I think the first thing to do is to solve, and then this would be plus negative I alpha. Because we've got two different moments of inertia, let's just solve for the total moment of inertia first. So this is I total. That would be 3 times MO times the radius squared. Now our radius here is going to be L, so that one is L squared. And then to that, we're going to add the moment of inertia of the other side. So the moment of inertia of the other side has got to be equal to MO times 2L squared, and that's that quantity squared. So our total moment of inertia is going to be 3MO L squared plus, and then 2 times 2 is 4, that would be 4MO L squared. And so that would be 7 times MO L squared. Now that we've got that, we can go back to our torque equation. So we've summed all these together, so we really don't need this equation. We're just going to say the overall torque is equal to the moment of inertia total times our angular acceleration. So let's go ahead and figure out our angular acceleration. Angular acceleration should be equal to the torque divided by the total moment of inertia. What is our total torque? Well, remember, torque really can just be the mass original times gravity times the length of the rod. And so, or that distance that we are from it. So here we're going to say M times O times GL, and we're going to divide that by the 7MOL squared. So at this point, we're going to get rid of things that are common. MO is common. We can get rid of 1L on top and then 1L on the bottom, and we're left with an answer of G over 7L. And so our answer here is G over 7L. And that's the way that this one would work. Alrighty, so let's, the reason that we could use, let's go back for just a second. We recognize that this thing is going to turn. We're just not really sure which way it's going to turn. So we're going to just use MGL because torque, remember, is equal to force times the distance. And our distance here is L, so this would just be the mass times gravity of one of the masses times that length. So that's really kind of where that torque equation comes from. A little bit confusing, but not too bad. For number 18, this one says, which of the following is a scalar? Momentum we know is not a scalar, so neither of these would work. Power, is it always positive or zero, or could it also be negative? Well, we know that work can be negative, and because it's negative, we can get rid of it. And then power is equal to work divided by time, and if work can be negative, then power can be negative. So the only answer left is going to be kinetic energy, which is a scalar which does not have any direction. And kinetic energy, because it's 1/2 mv squared, or because it's 1/2 I omega squared, can never be negative. So that has got to be your answer. For number 19, this is a problem. It's really kind of funny. No fisherman would do this. However, maybe a physics fisherman would. We have a long pole. That pole is not really got hardly any mass at all, so we're going to ignore its mass. And I've caught a fish. And I have two tackle boxes. I've got a tackle box of 3.5 kilograms, and then I've got really not another tackle box. This is a cooler, and it's 5 kilograms. So I hang both of those, knowing that this one's heavier than this one, and I'm assuming that the fish, wherever I put it, I can find its mass by using the sum of the torques. Really strange, I know, but nonetheless, so the sum here of the torques should be equal to 0 if the whole thing sets up. So I've got the torque of the tackle box, I have the torque of the fish, and I have the torque of the cooler, all three of those. This one will have a torque going in this direction, this one will be this direction, so both of these are positive torques because they're going clockwise. This one is negative because it's going counterclockwise, and I can just add all those torques together. Remember, torque is force times the radius, and so these are all at 90 degrees to the board itself, so we don't have to worry about sine of the angle. Let's look at the first one. So for our first torque, we have 3.5 kilograms. We're going to multiply that times gravity, which is 10, because remember it's a force, which is a mass times gravity, and then our radius, which is L over 4 plus L over 4, which is going to be 2L over 4, which is really just L over 2. To that, we're going to add the torque of the fish. So this is the weight of the fish, not the mass, but the weight, times its distance from the center, which is L over 4. And then we have to subtract the thing that's on the other side, which is 5 for the cooler times 10 times L over 2, and that's equal to 0. So let's go ahead and simplify. This would be 35 over 2 times L plus the weight of the fish times L over 4 minus 50 over 2 times L, and that should be equal to 0. 35 divided by 2 is 17.5 plus WL over 4 minus 25 times L, and that's equal to 0. Let's go ahead and move this to the other side and go ahead and do our math with the other two. Oops, that's 17.5 L. So when I take the 25 minus 17.5, I get negative 7.5 times L is equal to negative W times L over 4, where this W is weight, not omega, just weight. The negatives become positives. I'm going to take 7.5 times 4, and that is 30. These L's go away, and that's equal to the weight. Doesn't want weight, wants to know mass, so I just take my weight, divide it by gravity, that's equal to mass. And so now I end up with 3 kilograms for number 19. The last problem that we're going to do here is this one. This is number 20. I have two objects, one of 6 kilograms, one of 8 kilograms. They're hung from the end of a stick that is 70 centimeters long and has marks every 10 centimeters as shown above. If the mass of the stick we don't worry about, at what point should a cord be attached so that it will remain horizontal? This one's really kind of very simple to do. So here what we're going to do is look. We know that the very center is going to be where it does not balance. So we're not going to pick C. That cannot be right. This mass is heavier, and so because this mass is heavier, I've got to pick a point here that is to the right of our stick. 8 is not much bigger than 6, and so just by guesstimating, we can guess the right answer, and that would be D. If it's an E, it's probably too far over, and the 6 kilogram mass would end up being a little bit bigger. So let's go ahead and just figure out the torques. Let's figure out the torque at D for letter 6, for number 6 here. So that'd be 6 times 1, 2, 3, so we're actually 4 away. If we put it at D, 6 times 4 is 24, and 8 times 1, 2, 3 is 24. Aha! If this is 24 positive and this is 24 negative, then they do absolutely have to balance at that point. And that is the end of number 11 through number 20.